How's everybody doing?
Good, how are you?
Pretty good. So before I dive into this, just as a reminder, there's no class on Monday because of Martin Luther King Day. So does anyone have any questions before I dive into the lesson?
We're starting in person on Wednesday, right?
That is currently the plan.
Okay, cool.
So does that mean on Tuesday we'll be online for math?
There is no math class on Tuesday.
Tuesday, oh, sorry, Wednesday. Oh,
There's schools canceled on Monday. The next class after that is Wednesday, and that will be in person.
okay, perfect. Thank you.
No problem. Okay, so if I give you guys a graph, we can still do this function composition thing. We're going to use that second method that I was talking about before of just figuring out what is g of 3? So I look at g of 3. Well, it's going to be 4. And then I scroll up to see what f of 4 is. F of 4 is just 0. So f of g of 3 is going to be equal to 0. Does that make sense?
It does.
Cool. I'm just going to rewrite these on the side so that I don't have to keep scrolling. So using the same idea here with g of f. So now we're doing f first, right? Of 5, so that's a 1. And then I look at g of 1, that's 3. So somebody tell me what g of 1 is and then what f of g of 1 is.
Would FG of 1 be 3?
So g of 1 is 3, right? So then we have f of 3. And what's f of 3?
2.
Perfect. So f of 3 we just said is 2, right? So we have g of 2 now. So what's g of 2?
0.
Exactly. So does this make sense? Do people feel comfortable doing function composition on graphs?
Okay, I see it now.
Good. We can also do it on charts, which are basically the same idea, but you don't actually gets rid of a lot of the extra unnecessary information. So now we're doing f of g of 3. So it's g of 3 is 2. And then I do f of 2 is 8. And then similarly for this, doing g of f of 3. So f of 3 is 3. G of 3 is 2. Does that make sense to people?
For some reason, I'm not getting it. Would you be able to go over that one more time?
Sure. So let's I guess do another example. So let's do f of g of 1, right? So I check out what's g of 1. Well, g of 1 here is 3, right?
Okay.
So now I'm
Oh, and then f of 3 would be then 3.
exactly
Okay.
cool.
Wait, so when we're saying like G of whatever, F of whatever, are we looking in the X column or are we looking, because I was looking at the numbers like F of X underneath that and G of X underneath that.
So this is, we look into the X column to see then what the G is.
So like what corresponds to that? Okay, that makes sense.
Yeah, so this is saying that G of 3 is 2. Does that make sense?
Yeah, that makes more sense. I was just confused because you're like F of 3 and I looked at the, it doesn't matter. I get it now. Thanks.
Cool. Okay, so now we want to find the domain of a function composition. So this is basically, we're still asking, okay, what numbers can I validly plug in and get an answer out? But it becomes a little bit more complicated when I'm layering them. But the easiest way to do this is going to be to plug in do it as like f of, plug the function into the function rather than trying to do it in the way we were doing with the points. Remember from the end of the last class, we had the two different methods. One was we plug in the point and then plug in the point again. That's what we just did for those. The other was to just plug in, this is going to be equal to f of g of x. It's going to be equal to f of root 2x minus 5. And then everywhere I see an x, I replace it with root 2x minus 5. So this becomes equal to 1 over root 2x minus 5 all cubed. So now I look at this and I have two restrictions, right? So this is still a square root. The inside of a square root can't be negative, right? Or has to be greater than or equal to 0. So we have 2x minus 5 has to be greater than or equal to 0. And then we also have that we can't divide by 0. So that means that this guy can't be equal to 0. So what do we get? We get 2x is greater than or equal to 5. X is greater than or equal to 5 over 2. And over here, this becomes 2x minus 5 is not equal to 0. And that, again, through the same exact process, is going to give us x is not equal to 5 over 2. So it has to be greater than or equal, but not equal. So x just has to be strictly greater than 5 over 2.
Pardon me, Professor.
Sure.
Can you just get rid of a square root with a cube?
No, sorry, I guess I skipped a step. You do the cube root of both sides, and then you get square root of 2x minus 5 is not equal to 0.
Oh, and then you, okay.
Yeah.
So the cube root, and then you square both sides. Okay.
Yeah. So just when 0 is on the opposite side, you get to fudge things a little bit quicker. Like it's also, if you multiply by a constant, it doesn't change anything. But yeah, I should have done that out.
What are the cases that determine the domain?
So there's a few different things we need to remember. One of them is can't divide by 0. Can't divide by 0. You can divide by 6. And then another one that comes up very often is that the inside of the square root has to be greater than or equal to 0. You can't take the square root of a negative number. This is by far the most common thing that comes up, but actually if I give you any even root, so the fourth root, then that also has to be greater than or equal to 0. The sixth root also has to be greater than or equal to 0, but you can get the cube root. So if I give you the cube root of, let's say negative 27, that's just going to be equal to negative 3. So cube roots can be anything. square roots, fourth roots, sixth roots, blah, blah, those, the inside has to be greater than or equal to 0.
Okay, cool.
Pardon me, Professor.
Sure.
Your notation for the domain, x is greater than 5/2, would that be acceptable, or do we need to put what, like open parentheses, like 5/2, comma infinity, open parentheses or whatever?
So I was about to switch it into interval notation, but if I say put this in interval notation, then you have to put in the parentheses and brackets format. If I just say, what's the domain, then this is fine.
Okay.
So if I want to put this in interval notation, then I would have to do, I would change this to 5/2 to infinity, right? Because it has to be anything that's bigger than 5/2 can't be equal, so it's not the square bracket. And then it can be anything bigger, so it goes all the way up to infinity. Does this make sense to people? Cool. So if we do f of g of x here, that's going to be equal to 1 over x minus 1 over x plus 1. And this, when we divide by a fraction, it just ends up flipping that fraction. So that's going to be equal to x plus 1 divided by x minus 1. So what's the overriding rule here?
It can't equal 0.
Yeah, so we have to have this guy not equal to 0. So we'll have x is not equal to 1. So how would I write that as interval notation?
Open bracket, negative infinity to 1, open bracket, union, open bracket 1, comma infinity, open bracket.
Exactly. Perfect. Any questions about this stuff before we move on to the next section? Okay, so we want to find f of x and f of g of h for these guys. So you can compose a function with itself, perfectly valid. So what would that be? That would be f of x going to be equal to f of x squared. And everywhere I see an x, I replace it with x squared. So that becomes x squared is equal to x to the 4th. Does that make sense?
Oh yeah, just for my own review, when you're squaring like an exponent like this, do you add or multiply?
It becomes multiplication.
Okay.
So if this was like x cubed squared, this would be equal to x to the 6th.
Okay, thank you.
And then the addition comes when you do this. So this would become x to the 5th when you multiply them, which is another way you can think of this, like squaring is the same thing as multiplying by itself. So this is equal to x cubed times x cubed is equal to x to the 3 plus 3 is 6. Good question. Anything else before we do this little monstrosity? Okay. So f of g of h of x going to be equal to f of g of x cubed plus 1. That's going to be equal to, everywhere I see an x, I replace it x cubed plus 1. F of x cubed plus 1 plus 3. That, does that make sense to people?
Right, so because you square root the 8, I'm at the 4, and then you multiply the root 3.
Well, this is, are you talking about for this step?
Yes, does that work?
So this one is foiling. So this times this gives us x to the 6th, right? Because of that thing that we did before, x3 plus x3. X to the 3 times x to the 3 gives you x to the 6th. Followed by this plus 4x cubed plus 4x cubed plus 16.
Oh, okay.
Then we just combine like terms to get the 8. Does that make sense?
I see it now.
Cool. Okay, so reversing the process here. Sometimes we want to actually kind of view a given function as a composition of functions. There's like a natural way to do that sometimes. So if I have, sometimes there's one very natural way to do it. And other times there's multiple natural ways to do it. Other times it's just kind of no natural way to do it. So, but for this guy, what are people's thoughts for what's the natural way, a natural way to do this?
F of x is x to the 4th, and then g of x is square root of x to the 7th plus 5.
Yeah, that is probably the most natural way to do this by far. Especially considering that we didn't distribute this to the square root, because you could have simplified this to get x to the 7th plus 5 all squared, right? But considering we didn't simplify it that way, this is by far the most natural way of doing it. There are other ways we can do it. If you feel so inclined, but this is the most natural. What about for this guy? Any other ones? Anything that people think is comes to mind for them?
Would you try to break apart the x root 3? X to the 3rd?
Yeah, you could do something with x to the 3, definitely. So if you wanted to kind of take that as one of your functions, you could do g of x is equal to x to the 3. And then what would the f of x be? Kind of the opposite. Everywhere we see an x to the 3, we replace it with x.
Would it just be 4 over x plus 1?
Yeah. This is a perfectly valid way to do it. Not the first way that I thought of. The first way that I thought of was, we'll call this g prime of x is equal to x cubed plus 1, and then f prime of x is equal to 4 over x. Either of these works. Neither of them is really much more natural than the other, but you can do either of these. Any questions on this?
Yes, I don't really get the difference between, like, I know they're different, but I don't get how they're the same, if that makes sense. The two like, we did it one way and then the other way.
Well, they're the same when we get the composition out. So
Okay.
if I do f of g of x, I get 4 over x cubed plus 1. And also if I do f prime of g prime of x, I get 4 over x cubed plus 1. So when I say that they're the same, I just mean that like either of them is a valid solution for like decomposing this.
Okay. Can we think of the composition as like a separate function?
Yeah, the composition gives you a new function. Yeah,
Okay. All right. Thank you.
cool. So that kind of touched a little bit. I kind of touched a little bit on inverses there without actually talking about it. But the inverse functions are another important idea. So one of the things that we talk about with, if you guys have heard of inverse before, probably the most common way that you've heard of it is multiplicative inverse. So 2 times 1/2 gives you 1, so 1/2 is the multiplicative inverse of 2. Might also have heard of the additive inverse, which is just the negative. So if I have 3 plus -3, that's equal to 0. So this is the additive inverse. The thing that you do to this to cancel it out. You can generalize these a bit more to the idea of functions, right? So there is the additive inverse of x squared plus 1 is equal to just negative x squared plus 1. And then if we have x cubed, the multiplicative inverse is just going to be x to the -3 or 1 over x cubed, right? It's the same idea as this. We're just dealing with functions now instead of just variable numbers. And this is the same idea as this. We're just dealing with functions again instead of numbers. Your functions additive inverse or multiplicative inverse. So, but we can also talk about the inverse with respect to composition. So when I was looking at the multiplicative inverse, what was I trying to get back to?
1.
Yeah. So when I multiplicative inverse gets me back to 1. What does the additive inverse get you back to?
0.
Yeah. And the reason is that this is what's called a multiplicative identity, which means that if you multiply something by 1, it doesn't do anything, right? And this is what's called the additive identity, which means that if you add 0 to anything, it doesn't change anything. Turns out that there's another one. There's a function that is the identity under composition. So meaning that if you compose this with something, it doesn't do anything. Does somebody want to guess what that is? f of x equals x, right? Because if I give you, let's say, g of x is equal to x cubed plus 1, what is f of g of x? Well, everywhere I see an x, I replace it with x cubed plus 3. So that's just g of x, right? And it'll be the same thing if you do g of f of x. Then this is just g of x, because f of x is x. And that's going to be equal to x cubed plus 1. So if we
So it's when
compose
one of
something,
them,
sorry,
so it's when one of them equals x, because this is really kind of just weird.
yes, yeah, it is. This should feel a little bit weird, but I'm just trying to get you to kind of have a more general idea of why we're trying to get back to just x. So it's not just like this is the definition. It's like, hey, there's something very natural about it being we're trying to get it back to x. But this has a very natural idea with the idea with composition of functions. But if so, this is the thing that we're trying to get back to. We're trying to find the inverse now is just whatever I compose this with that gets me back to just x. It gets me back to the identity, just like how I multiplied by 1/2 to get me back to the multiplicative identity for 2, or I added -3 to get me back to the additive identity for 0, for 3 there. So if this doesn't make sense, don't worry too much yet. But the important thing for us to do is we're trying to find a function that when we compose it with f, we get back to just x. So there's a few things that we need to do to make sure that this can even exist. First off, our function has to be 1-to-1, meaning that you can't have something like this, because then if I like if I give you x squared, that's not 1-to-1 because 2 and -2 both map to 4. And if I look at the inverse function, that's not going to be able to get me back to just regular old x, because it'll map this guy and this guy to the same thing. And x maps x is just 1-to-1. F of x equals x is 1-to-1. So we need it if we don't have a 1-to-1 function. So if it fails the horizontal line test, then we don't have an inverse function. So
Pardon me.
Sure.
By 1-to-1, I feel like I'm hearing conflicting things. By 1-to-1, you're saying it can't be exponential, but it also has to pass the vertical line test, right?
Well, so if it's a function, it already passes the vertical line test.
Okay.
And so exponential is something else, right? So exponential is like 2 to the x.
Yeah.
As opposed to x squared. 2 to the x actually is fine. So this would be like 2 to the x right here. And that passes the horizontal line test.
Okay, so it's a horizontal line test now. Okay.
Yeah, so it's the horizontal line test is just saying, hey, if I like this passes because it only passes through at most 1 point for every x value, but this one would fail because if I do because it would pass through 2 separate lines or 2 separate points. Does that make sense?
Yeah.
Okay, cool. And the reason is, so if we have f of x equals y, then f inverse of y is going to be equal to x. So if you have two different points, if you have f of x2 is also equal to y, then this guy can only map to one thing.
So it can only cancel out one of the points.
Yeah. So it kind of ends up being the horizontal line test kind of ends up being a vertical line test on the inverse function.
Mhm.
So
Thank you.
no problem. So we want to verify that these guys are inverses of each other. So we can just do the composition, right? So this tells me that f of x is an inverse function of t of x. If you want me to do it the other direction, you get the same thing out. But does this make sense to people?
Yeah, if it works one way, do you need to do it both ways? Like, are there
No,
instances? Okay,
assuming that it passes the horizontal line test, you'll be fine. The only weird thing is you can get like something that looks like this and this, but you get a half inverse where this side corresponds to the inverse for this, but you don't have to worry about that. If you just plug it in one way, you'll be fine.
okay, thanks.
So this one we'll do f of So this is how the algebra here simplifies and shows you that these guys are inverses. If you want, you can do it the other way, but you don't have to. I'll do this as an example though. So if we were to do this, we would get, well, does this make sense? So sometimes the algebra will be a lot easier in one direction than the other. So it might make sense to do it in one direction, but should either direction should work. Does this make sense? Cool. So I'm just gonna let you guys do this last one. And then, so this right here, if we want to sketch the inverse of this, well, then we'll have, so -3 and 5. So what we've got this point, we've got -3, 0, got, sorry, 0, 1. Got 1, 3, and we got 5, 5. So what do people think we're going to do for this? Hint, remember when I said if f of x equals y, inverse of x, sorry, and f inverse of y is equal to x. So if I'm mapping the inverse, what am I doing with these points?
So is it just putting a 1 over all of them?
Not a 1 over, but
Well, like a 1 over -3.
not quite. You're thinking of the wrong type of inverting. That would give you the multiplicative inverse. But we're doing the function inverse.
No idea.
We're just going to switch the order of all of these points. Right? Because we have f of x equals y implies that f of y equals x for the f inverse of y equals x. So that would mean that f inverse of -3 is equal to -5. And f inverse of 0 is going to be equal to -3. Inverse of 1 is going to be 0. F inverse of 3 is going to be 1. And f inverse of 5 is going to be 5. Does this make sense to people?
I think it does.
Huh?
I said I think it makes sense to me. You just flip it around against the inverse, right? The points.
Yeah, exactly. So we're going to get -3, -5 here. It's going to be 1 point, and then we'll get 0, -3. It's going to be the next point, and we're just going to draw a line between them because it's linear between those, and the inverse function of a line is a line. 1, 0. 3, 1. And 5, 5. Does this make sense?
Would we be able to plug in a couple of the points on the original into the whatever that weirdness on the right is, to like actually see how it mathematically works? Because like I can take your word for it, but I'd rather like understand it, because it's still a little bit off for me.
This is just one of the ways of defining the inverse, right? So, I mean, like, this is going to be the inverse, like the kind of the definition of the inverse, because if we have f of f inverse of x, we need to get x out, right? Actually, let's switch the order there. We have f inverse of f of x, we need to get x out, right? But f of x here is y, right? So f inverse of y has to be equal to x. And like this is just one of the ways that we can define the inverse. Or you can take it as just like a quick consequence of doing this thing right here, and like just naming what f of x is, as just naming f of x as y. But if we do that, then this switcheroo operation just becomes very natural. It just becomes like your x's become your y's and your y's become your x's, because your y is now your input and your x is your output for your inverse. Does that make sense?
Okay, that does make sense.
Okay.
The output is the input, but then the input is the, okay.
Yeah. Cool. So the inverse operation for y equals x cubed is just going to be the cube root of x. And that's just because, you know, you get the if you do the cube root of x cubed, you get x. Does this function have an inverse?
No, because the horizontal line test.
Exactly. This goes through several points, therefore it is not does not have an inverse. Yeah, so this one will be, this one will not be. And if you just picture what the functions look like, that'll be pretty clear. So we have like an actual method for step-by-step solving for the inverse. And the first thing is we're just going to get rid of that f of x, and we're going to replace it with either you can think of it as this becomes x, and then you replace all of the y's on this, x's on this side with y's, or you can think of it as an extra step of we have y is equal to x over 3 minus 5, and then you do the switch of the x's and the y's. So this becomes x equals y over 3 minus 5, and now we solve for y in terms of x. So we get x plus 5 equal to y over 3, because we add 5 to both sides, and then we multiply both sides by 3 to get y by itself. We get y is equal to 3x plus 5. And then this is going to be the inverse function. You guys can check that yourselves. If I had a bit more time, I would run through the algebra, but you can see that this right here is going to be the inverse function for that. Does that make sense to people?
Yeah.
Wait, sorry, did you say yes or no?
Oh, I said yes. I'm sorry, was I speaking too long?
Cool, no problem, thank you. Yeah, so I'll just do these two problems and then we'll call it a day. Stick around to answer any questions anyone has. So then we get this run becomes x is equal to 6y plus 12. So we get x minus 12, 6y, bless you,
Gotcha.
is equal to, then we divide both sides by 6, we get x over 6 minus 2 is equal to y. So we get f inverse of x is equal to x over 6 minus 2. And this one's pretty easy to plug in and check. If you do f of f inverse x, you get 6 times x over 6 minus 2 plus 12 is equal to x minus 12 plus 12. Cool. It's not just for lines, it should work for this guy too. This is invertible. If it's got a cube root, it's probably invertible. Unless there's something that would make it not invertible on the inside. So if you had like cube root of x squared, that wouldn't be because x squared is not invertible, but cube root of something that's invertible will be invertible. So we do x is equal to 3 cube root of y plus 2. This becomes x over 3 is equal to cube root of y plus 2. Now we cube both sides and we get x cubed over 27 is equal to y plus 2. We get y is equal to x cubed over 27 minus 2. Does that make sense?
It makes sense to me.
Cool. So it'll be the same deal with these guys. You can run through and check them. And there's plenty of extra problems here if you want to try your hand at them. But I'm going to call it a day for now. I'll stick around and answer any questions if anyone wants to ask them. Have a good long weekend and see you in person on Wednesday, assuming nothing
Have a good
changes.
weekend.
You too.
Thank you.
Hey, pardon me, Professor.
Sure.
When do we get the results back for our homework?
That would